Good afternoon. In this class, we will be seeing linear non-homogeneous recurrence relation with constant coefficients. So, in the earlier class, we have seen linear homogeneous recurrence relations. So, we did not see this part. We had seen linear homogeneous recurrence relations with constant coefficients. So, for solving simply linear homogeneous recurrence relation, we have simplified it and we have seen it with the four theorems. So we have studied four theorems for solving different kinds of linear homogeneous recurrence relations. Now, in this class, we will see non-homogeneous. Now, if you recall your first part of this unit, I explained all these terms and I mentioned what non-homogeneous means. Whenever you have a function of n in such that the earlier terms are not similar to this function of n, then it is known as non-homogeneous. So that is whenever your recurrence relation contains some term f of n that depends only on n not on any ai values. A1, A2, A3 are generally used for an, an minus 1 in terms of this. Our function of n does not depend on an or an minus 1, it is simply dependent on n. So in that case, we call it as linear non-homogeneous recurrence relation. For the explanation on homogeneous and linear and all these terms, please refer to the first video of this unit 3. So now, whenever we are talking about linear non-homogeneous recurrence relation with constant coefficient, so they contain some terms such as this f of n that depend only on n. In that case, the general form of our equation will be an c1 an minus 1 plus c2 an minus 2. It's mentioned here, so let me just write it over here. a1 an c1 an minus 1 plus c2 an minus 2 plus and so on up to ck an minus k. We may have one term over here, two terms, or k terms. There will be a function of n that depends only on n, not on this f of n. Okay, this is the general form of your linear non-homogeneous recurrence relation. Now, for these linear non-homogeneous recurrence relations, you already know that C1, C2, and so on up to Ck are all real numbers. So they are all real numbers. This we have already studied with respect to the earlier one, linear homogeneous recurrence relation, and f of n is dependent only on n. Now, this part of the equation, that is the one I have underlined or given with the help of a bracket, this is known as associated homogeneous recurrence relation. Associated because it is homogeneous. If we don't consider this term, this part is homogeneous. So that is why we are calling it associated homogeneous recurrence relation. And this is very important. It is actually very important when we want to find the solution for our linear non-homogeneous recurrence relation. And one example, if you want, can be given as an is equal to 3an minus 1. If this was an example, then we call it as homogeneous recurrence relation because we don't have anything which is dependent only on n. So this is linear homogeneous recurrence relation. But suppose if I add 2 power n or 2n or 5n or simply n square, then it will be non-homogeneous. So let me just erase this. Yeah. So now it will be non-homogeneous. So this equation n is equal to 3an minus 1 plus power n is linear non-homogeneous recurrence relation with constant coefficient. Now, what is the reason we are calling it as linear non-homogeneous recurrence relation with constant coefficients? First and foremost, we have this value over here, f of n. This is f of n. This is our f of n. So in this case, we have this function which is dependent only on n and not on the en terms. and this is known as linear non-homogeneous. So for these solutions, we can't use the four theorems that we have studied earlier. That is, we cannot consider them as the general equation and then find the root, etc. What we have used in that earlier case. Now for this case, we will have to have another solution which will be given as follows. So in the next slide, you will be seeing that. So solution of linear non-homogeneous recurrence relation with constant coefficient. So this is just a short form actually, but this means non-homogeneous. Non-homogeneous. Now in this case, suppose before seeing this, the solution, we will see just a few examples so that we understand the associated a bit in detail. So let's see. Suppose the recurrent relations an is equal to a minus 1 plus 2 power n. A is equal to an minus 1 plus an minus 2 plus n squared plus n plus 1. An is equal to 3an minus 1 plus n into the power n. An is equal to an minus 1 plus an minus 2 plus n minus 3 plus n factorial. All these are linear non-homogeneous recurrence relations with constant coefficients. Okay. Now, in this case, what is the reason they are linear non-homogeneous? Because we have these terms in each case. Now, the question is, what are the associated linear non-homogeneous recurrence relations? What are the associated homogeneous recurrence relation in each case? So in this case, just underline the associated homogeneous recurrence relation. So we have this is associated homogeneous recurrence relation in the first case. In the second case, you have to exclude the terms which do not contain this n. So that means these terms will be excluded, and this is your associated homogeneous recurrence relation. Just let me draw this. Yeah. And in the third case, you can identify this is the associated homogeneous recurrence relation. And in the final case, you have till an minus 3. By now, I hope you have understood the concept. Now, let's proceed to the solution of this kind of problem. Now, when we want to find the solution of a non-homogeneous recurrence relation, we can understand one thing, or this will be actually easier to understand, but whenever we want to find a solution, it will be the sum of two things. So because we have two parts in our homogeneous relation, the associated part and the other is the function of n. So for this solution, we will have it in two parts. One will be the solution. One will be the solution of the associated part and the solution of your function of n. So this theorem 5. So we'll be continuing with the same sequence, that is theorem 5. So the four theorems, you have to remember that the first four theorems are for homogeneous and the fifth theorem is for non-homogeneous. Now in this case, if a of n of p is a particular solution to the linear non-homogeneous recurrence relation, then an is equal to C1 an minus 1. So instead of writing the entire thing, C1 an minus 1 plus C2 an minus 2 until we go on up to Ck an minus k, Instead of that, I have shortened it in this way, that is I is equal to 1 to k ci a n minus I plus f of n. Okay, so this, for this every solution, it is of the form an of p plus an of h. Now what is an of p and what is an of h? An of p is here particular solution for the linear non-homogeneous recurrence relation. Okay, but what is this an of h? An of h is the solution for your associated recurrence relation, that is your an is equal to c1 an minus 1. I'm just writing it completely instead of the shortened or the abbreviated form. So this will be an of h is the solution for homogeneous recurrence relation, and it is given in this way: c1 an minus 1 plus c2 an minus 2, the same thing, plus and so on up to ck an minus k. So this an of h is the solution for our homogeneous part, and this is the way you use the solution. Now for the same, we will see an example. So instead of doing it over here, I'll try to do it on a whiteboard. So find all the solutions to an is equal to 3an minus 1 plus 2n, which for which the solution, what is the solution with a1? So this is our initial condition. If you remember the concept of initial condition, a1 is given as 3. Okay, so for this, let's do it over here. The question is an is equal to 3an minus 1 plus 2n. Now, to solve this linear non-homogeneous recurrence relation with constant coefficients, this is n minus 1, just let me change it, n minus 1. We need to solve its associated linear homogeneous equation and to find a particular solution for the given non-homogeneous equation. So what is the associated linear homogeneous equation? Let me just write it. So for the associated linear homogeneous equation for this problem is an is equal to 3an minus 1. That is, we have to exclude the function of n. And what are the solutions? So every time each term will be multiplied with 3. So suppose a1 is 3 or a1 is 2. Let's take the initial condition of our example. So it is given that a1 is equal to 3. So a1 is 3, then a2 will be 3 into 3 and so on. Each time we are multiplying with 3. So the general equation or the general solution will be given as an of h is given as alpha into 3 power n. Okay, where your alpha is a constant. Okay, so alpha is given as a constant. Now we have to find a particular solution. Okay, we need the particular solution. I have found, so first understand this. This is the first step. I need to find the homogeneous equation, this part's solution. So that will be simply multiplying with 3 power n, and we have to take a constant alpha. Now for this is your second part. You have to find a particular solution. Now because what is our f of n given as? F of n is equal to 2n. What is this 2n? It is a polynomial equation of degree 1. That is polynomial in degree 1. And for this we can easily say that, suppose if we want to take a trial solution, and it can be taken as Pn is equal to Cn plus d, where both C and D are constant. C and D are constant. To determine whether there are any solutions of this form, suppose that Pn is equal to Cn plus D, this is a solution. Then the equation En is equal to 3an minus 1 plus 2n, it can be written as, so instead of an we will write this pn. Okay, so let me just write it over here. En is being replaced by this value, that's it. Okay, nothing complicated. So if we have an, we will write cn plus d. If we have an minus 1, we will write c into n minus 1 plus d. Okay, so now this can be written as the equation, our original equation. I'll just point it out here. It is being written as cn plus d is equal to 3 into c into n minus 1 plus d. Why am I writing n minus 1? Because we have a n minus 1 over here, plus 2n. Now we will solve this equation completely, bring all the terms to one side and equate it to 0. So when we do that, we will get, let me just do it completely, 3 into 3cn minus 3 plus 3d plus 2n. Okay. After that, it can be written as, let's bring these terms to this side. So we will have 3cn minus cn plus 3d plus, actually minus, since here we have a plus, this will change to minus. So minus d plus 2n minus 3 minus 3, actually this will be when we multiply c, so minus 3c. So minus 3c is equal to 0. I'll just write it better over here. So 3cn minus cn is 2cn. We'll bring the n terms to one side so we can take n common. So 2cn plus 2n. 3d minus d is 2d. Minus, this is 3c. So minus 3c is equal to 0. Now after that, let's take the n common. 2 plus 2c into n plus 2d minus 3c is equal to 0. If you remember, c and d both are constants. We took cn plus d, n is the term, c and d are constants. So this is our cn plus d solution. So if you look, this is the c part. Okay, this is also a constant. We are multiplying with n, and this is also a constant. Now, if and only if, now this becomes a solution if 2 plus 2c is equal to 0 and 2d minus 3c is equal to 0. Okay. Now we will find the c value from here. C is equal to, this will be minus 2 divided by 2 will be minus 1. And if we substitute minus 1 in this equation, we will get d is equal to minus 3 by 2. Then what will our an of p becomes? An of p will be, our actual equation was cn plus d. So instead of cn plus d, we have to substitute the c and d value. So it will be minus n minus 3 by 2. This is the particular solution for our f of n. Now, by using the theorem, we know that our theorem stated that we have to add both the solutions. An was an of p plus an of h. Okay. So an of h, if you remember, was alpha into 3n. The first thing that I did, the first step. Now, this is by using theorem 5. So let me just mention that by theorem 5. So we will write the entire thing, minus n minus 3 by 2 plus, what is this part, alpha into 3 power n, where we know that alpha is a constant, where alpha is a constant. Now we need to find the value of alpha. To find the solution with a1 is equal to 3, So let's do that. So we know that A1 is given as 3. A1 is 3. So substitute the value and let n is equal to 1. Alright. So this can be written as A1 is equal to n is 1 we are taking, so minus 1 minus 3 by 2 plus alpha into 3 power 1. A1 is also given as 3. 3 is equal to minus 1 minus 3 by 2 plus alpha into 3. Then if we solve this equation for alpha, the value will be 11 by 6. So alpha value we have obtained. Now let's go back to our equation, and instead of this, okay, I'm writing here by just clearing, striking this off, but in your notes, please write finally over here, okay, because it is easier to understand. I'm just writing it over here. So your final solution will be minus n minus 3 by 2 plus 11 by 6 into 3n. So this is an example problem by using theorem 5. Now after that, let's take another example. Find all solutions of the recurrence relation. An is equal, this is the question. So An is given as 5an minus 1 plus 6an minus 2 plus 7 power n. Okay. Now in this case, initial conditions are not given. So if we have alpha and beta in our equation, they will remain as it is. So we can identify that this is a linear non-homogeneous recurrence relation. And what is the associated homogeneous recurrence relation? I'll just mention it over here. Associated homogeneous recurrence relation is given as An is equal to 5an minus 1 minus 6an minus 2. Now if you solve it, we will be using theorem 1, I believe. An minus 5an minus 1 plus 6an minus 2 is equal to 0. Then when we get the roots will be 2 and 3. So yes, if we convert it into r square minus 5r plus 6, and then if you find the roots, basically the roots will be 2 and 3. Please solve it by yourself. You have to do the entire steps in the examination. R1 is equal to 2 and R2 is equal to 3. Okay. So our An of H will be alpha 1 into 2 power n plus alpha 2 into 3 power n, where alpha 1 and alpha 2 are constant. Now we have f of n is given as 7. F of n is given as 7 power n. Let me just write f of n. F of n is given as 7 power n and a trial solution. So we need to find the solution. So what we do is we use a trial method, and we see that the trial solution will be An of p can be c into 7 power n, where your c is given as a constant. So in our earlier example, we took cn plus d. The reason being we had multiplication 2 into n, but here since we have power of n, our terms will be in powers of n only. So we just need one c as a constant. Now to substitute this in our equation, so instead of an, we will be substituting c into 7 power n. So let's just substitute it. So c into 7 power n, instead of an minus 1, c into 7 power n minus 1. So 5 into c into 7 power n minus 1. Here c into 7 power n minus 2. Okay. So c into 7 power n minus 2 plus 7 power n. Now just cancel the 7, divide the entire equation by 7 power n minus 2, how we generally do it. We will get 49c. Here we will be left with dividing the equation with 7 power n minus 2. I am just writing it over here. This is very, very important. So when we divide 7 power n by 7 power n minus 2, we will be left with 7 square, which is equivalent to 49. So 49c, here we will be left with 7. So 5 into 7 will be 35. 35c, or better, let me divide it and show you. Okay. So when we divide the entire equation by 7 power n minus 2, let's divide it by 7 power n minus 2. Then we cancel, we get over here 7 square, which is 49. 5 into c into 7 power n minus 1 by 7 power n minus 2. We are simply left with 7, so 535. This will be into 7 power n minus 2 by 7 power n minus 2, completely cancelled. Then again this will be left with 7 square. So now we can write this equation as 49c is equal to 35c minus 6c plus 49. Now if you solve this completely, you will get c value, which will be 49 by 20. Hence our solution an of p, which we have taken, let me mention it over here, this will be becoming, instead of c, let's write 49 by 20. So 49 by 20 into 7 power n. All. This is the particular solution, and over here we got the so this is our particular solution. Let me just write it. Particular solution an of p, and this was our homogeneous solution. So now an will be simply given as an is equal to an of p plus an of h. So if we take that, then it will be, what is an of p? Alpha 1 into 3 power n plus alpha 2 into, okay, I took r1 as 2, I believe. So let's just alpha 1 into 3 power 2 power n plus alpha 2 into 3 power n, let's just check it, yeah. Then plus 49 by 20 into 7 power n. This is our solution. If we were given an initial condition, we can find the values of alpha 1 and alpha 2. But since we have not been given the initial conditions, we cannot find the values of alpha 1 and alpha 2. We will leave it as it is. This is the general solution for our problem. An is equal to 5an minus 1 plus 6an minus 2 plus 7 power n. So this concludes our topic of theorem 5.